Great. So we can't see my face, but my name is Clare Rainey. I am an academic and researcher from Ulster University in Northern Ireland, and thank you so much, Jordan, for asking me here today. It's really great, and it's good to see so many participants for a topic that I think is just so important in clinical practice at the minute. So my research area is on predominantly on AI in radiology and the impact of user interface design on user interaction. So my research area is predominantly in human computer interaction. So apologies, I seem to be having a few technical issues here, but hopefully we're okay. So I want to just have a wee chat with you. First of all, I suppose about the struggle of vision and how we're predominantly obviously talking about computer vision when we think about sort of the image interpretation tasks that we undertake in radiology, and that's what I'm going to focus on today. So vision really obviously is kind of the two-step kind of detection interpretation task or process was traditionally assumed to be a function of animates, and for many years, attempts at developing systems where computers could detect and accurately discern objects was a very limited success, and early attempts were kind of familiar with, where we have human programmed shape and pattern identification systems. So where humans would determine the characteristics of the object that made them determine what it was. But we know that there's so much more to that process as humans of vision, and many of the features of something that we identify aren't explicit even to ourselves. So we were talking, Jordan was identifying a little bit about the black box systems of artificial intelligence, and the recognition that as humans we're a bit of a black box as well. A real turning point then came with the ImageNet challenge in sort of 2012, 2014. And the ImageNet challenge, as many of us know, was a computer vision competition using a huge data set of labeled common objects. For instance, animals, everyday objects, and these were labeled by the public and had a reliable ground truth then. So developers then were set the task of competing for the highest accuracy, or agreement with the label for each of the objects in this test set. And we all many of us will be familiar with the fact that AlexNet, a convolutional neural network, far outperformed any others, and really provided then an example for this type of technology, which we are now so familiar with, but actually sort of in the grand scheme of things is still fairly recent. And it provided an example, I suppose, of this type of system to be used in computer vision tasks more generally. So I've sort of put up a little bit of a slide here just of the paper that was produced as part of that, and other big names on that. The godfather of AI, Geoffrey Hinton, was one of the main players in that as well. But neural networks weren't new at that stage. This was just sort of a springboard for their application in particular tasks. And neural networks themselves are computer systems based loosely on the function of the human brain. They use sort of a series of interconnected nodes, loosely based on neurons, and they process and make sense of the detected image and then produce an outcome. And an artificial neural network will forward process this input to an output, determine the accuracy of this, and then adjust weights and various other things, various other sort of attributions within the system itself until it reaches an acceptable accuracy. So it will try and then try again, much the same as we do as humans. A convolutional neural net like AlexNet works a little bit differently than this. There's more complexity. I've simplified it way too much there. But a convolutional neural network will basically apply a series of layers to an image input. We'll extract features then from this and then to reach the desired output. And they're particularly good at identification of objects because they have the ability of spatial discernment as well. So they're suited to objects on image rather what we need in computer vision. So already Jordan was talking about sort of the kind of AI hierarchy, and convolutional neural networks fall under the deep learning category of AI. And what I'm going to do today is talk a little bit about some of the inherent problems then that we have with that. Um, the deep learning systems generally are deep, as in they have lots of layers. They have a good bit of the processing takes place within hidden layers, and they also have an increased performance though based on that. So we'll discuss some of the problems related to that. So the complexity of the model means that with this processing taking place within hidden layers, the layers will the layers within the black box, or the hidden layers of the system, are the bits that will iteratively adjust parameters to reach that desired output. And in many cases, the use of computer vision models for classification and detection tasks will be to obtain agreement with a pre-labeled output by a human in the case of supervised learning, as Jordan was saying. So, ground truth is established, then the model is trained, and then the acceptable level then is determined based on that agreement with it. So to simplify it massively, basically what happens within a convolutional neural network is a digitized input image is presented here on the left-hand side of the screen. A digitized input image is presented to the system. The convolutional neural net, or the convolutional layer, sorry, within with the neurons within that, will extract features. This is also known as a kernel. And the features will then process onto a pooling layer, and the pooling layer then downsizes all these features produced, and it does that by reducing their spatial dimensions. This is then followed by activation functions, and the activation functions determine the relationships between these features. And then it's fed onto the fully connected layers, which is then fed onto the output. And the output could be, I've given a couple of examples here. It could be classification, segmentation, detection. I mean, this is really, really basic, this diagram that I've given here. And there are many, many advances and different architectures of convolutional neural networks even being developed now. Some of which you might see are recurrent neural networks, residual nets called res nets, and dense nets as well, densely connected, or dense CNNs. So I sort of briefly mentioned there that neural networks aren't necessarily new, but why has there been such a recent explosion in the use of AI in sort of life in general, and obviously in healthcare and computer vision specifically? The perceptron was first described in the 1950s, and it was really a single layer neural network based on the function of the human brain. But there were problems with this in terms of scaling up, and the networks weren't able to, these perceptron layers weren't able to scale up into multi-layer systems. And this actually, following this, when they realized sort of the problems with scale, sort of was one of the things that precipitated an AI winter around that time. So there wasn't much research done in this area until into the 1990s, and research in this area sort of started up again. By the 1990s, things had obviously changed in terms of technology, and the supporting technology had at that stage and continues to develop. So we're now in a position where we're able to eliminate a lot of the original problems associated with the limitations of using neural networks. So recent years has given rise to massively increased storage capability with massively decreased costs as well, and cloud storage capability as well, which has really helped. Digitized images being normal now has allowed us to have a good volume of really good quality and multiple data sets. So deep learning models are reliant on the volume of quality data presented to them. So if these models are learning by example, the more good quality examples, the better. So we're becoming increasingly aware of this and the need for labeled data sets for training models. And competitions such as the RSNA challenges, which I'm sure you'll be familiar with, the brain hemorrhage challenge, for instance, being one just example of that, and targeted data set production for research, such as the Mira data set from Stanford in 2019. And that's one that I'm going to describe a little bit later on. So in order to get a model, in order to produce a model which is generalizable and has multi-center application, we need multiple data sets from different clinical sources, as Jordan was alluding to as well, from different clinical sources, different pieces of equipment being used, different pathological presentations, and with a great level of diversity, as great a level of diversity as possible, with good quality labels, because the quality going in is going to be the quality that you have coming out. You've heard the phrase, garbage in, garbage out, but I like to be a little bit more optimistic and say quality in, quality out. Also, in recent years, there's been a real drive to improve processing units, and this is in some part driven by the very lucrative gaming industry. And this has resulted in faster graphics processing units. The reason this is important is because graphics processing units can be used with convolutional neural networks to really increase the speed of training and processing, and allowing the neural networks to scale up really, really well. And graphics processing units are really ideal at handling huge quantities of data, which is what we need for computer vision tasks. So in this landscape that we have together, we can leverage neural networks as an acceptable and actually excellent processing time, allowing training and processing of huge data sets, the importance of the quality of which are being increasingly recognized. And therefore, then the production of these is being promoted to access into these large volumes of data that we have present already in digital format in storage. So as I mentioned before, part of the processing of these advanced systems is really complex, and the performance of the model is determined usually by the systems reaching an acceptable performance or agreement with that ground truth that we've already established. The complexity of deep learning systems is really what permits their impressive performances. So these systems are developed adjusting certain aspects of their architecture, adjusting the importance of the attribution or weighting assigned to specific nodes to the accepted output. So for instance, by a back propagation mechanism, improving the model then iteratively as it goes along to reach an acceptable level of agreement, which is determined then by the expert user at the end, by the domain expert. And the mechanism by which this is accomplished varies, but usually when you increase the number of hidden layers, you will increase the performance of the model. So there's therefore a bit of a balance that has to go on between the opacity of the model. So for instance, black box models with their many hidden layers and sort of the opacity of that, which we might need to accept, or white box models. So for instance, decision trees. So whilst high performance is generally associated with deep learning and interpretable expert systems, sometimes referred to good old-fashioned AI, tend to exhibit a much lower performance on complex tasks. But the balance comes when the decision is associated with higher risk decisions. So for example, in healthcare, and this is where the human user really needs to accept responsibility for the decision, and that the decision that's being made by the AI will have an impact on the human or the patient at the end of it. So in certain instances, a more interpretable model may be the only option. And the user then has to be willing to accept a lower performance to allow them to be able to sort of stand over the AI output or to rely on the AI output. And this would have been the case with types of mammography CAD being used in the 80s and 90s, where we were able to understand that the system may overcall, but we could accept this because we were able to understand how the system was going wrong. And as I mentioned, when this is not the case with deep learning systems, is when mistakes are made, sometimes it isn't understandable why it does it. But in addition to this, and sort of the focus of my research is then when you add humans into the mix as well. So we've talked a lot about sort of AI systems, and certainly this tends to be the stuff that's flooding the literature about performance and new AI models being developed and things. But when we add humans into the mix, obviously that increases the complexity of everything. So in addition to sort of the decisions that you're making about acceptable transparency of the system that you use, there's issues then that we need to be aware of with the human who's interacting with these systems. And indeed, actually, the variation in the human response related to sort of still unknown factors such as level of clinical experience, level of use of advanced systems in daily life, and age, to name but a very few that are being investigated in the literature at the minute. So we're already aware of a lot of human biases, and these are sort of ones that I've drawn out of a couple of sources relating to radiology and image interpretation. But we're realizing that there are other biases associated with AI itself. I'm just really briefly going to go through because I know Jordan has alluded to these in his initial presentation. So, and I know I'm sort of a bit short on time here as well. So we have algorithmic biases which are inherent and embedded into the design of the system itself. It might be to do with, say, poor quality of the training data, or bias even of the AI designers of the social setting in which the model is being used. And it sort of highlights the earlier point of the requirement for large, diverse data sets and training. So in the example offered here, I've talked about a hiring system based on historical data, and problems in how the hiring process was conducted then are perpetuated through a system being trained on this data. Related to this, then following on from this, is data bias, when the bias results from the characteristics of the inputted data itself. And that's something we're becoming more and more aware of, and something that you'll see in the literature. And again, importance of using large, really good quality data sets. Societal bias, again, related to the other two biases which are mentioned and under the umbrella of algorithmic bias, but related to the landscape in which the AI system is used. But this is related directly to the context of the deployment. So an AI deployed in a non-diverse social context, there may not be so much societal bias, but that doesn't mirror real life at all, and shouldn't do, and could potentially be harmful. So my work focuses predominantly on the field of human-computer interaction, which is and the bit that I look at is a pretty narrow corner then of this, and the issue of bias in AI. And I focused for a long number of years in attempting to quantify some of the extent of the human interaction with advanced technologies generally. And I use black box AI systems and different examples of AI feedback to sort of delve into the factors which might impact the balance between over-reliance and underuse. And sort of on either side of that scale, there's automation bias, and then on the other side of that scale, there's associated risks of algorithmic aversion and lack of trust as well. But neither type of these interactions will lead to optimal use of the technology in the clinical setting. So automation bias, in case you haven't already heard of it, I'm sure you maybe have, but refers to the sort of tendency of the user to follow the AI feedback over one's own contradictory opinion. So, and over time, the problem of this might be into the future is with the absence of any consequence, might result in automation complacency, where the reliance on AI is so great that the user becomes totally reliant on the system, and may result in de-skilling in certain areas. Algorithmic aversion, on the other hand, then is the tendency of the user to mistrust or avoid the use of the technology entirely, and might then miss out on the additional benefits of the system. So a really common example, which I had sort of heard of this week, was somebody electing not to follow the sat nav. We were both going to the same. We both had to arrive in the same place at the same time, coming from the same place, and my friends arrived half an hour later because they thought they knew better than the sat nav, whereas I blindly followed it down every side road, but managed to get there quicker. The human-computer interaction research is really beginning to shed some light in the context and sort of the environment surrounding these particular situations. And it's allowing then users of AI to examine themselves as well and see where they might fall. So in order to mitigate against trust issues in recent years, as Jordan has mentioned, there's been a really great focus on the use of explainable AI and the use of heat maps as one example to represent to the user in human comprehensible format the processes of that complex AI decision making. And this can take many formats. I've used heat maps as an example in my research, but it could be a PhD student of mine is using regions of interest and textual descriptions, as well as sort of box plots and things too. So the first study that I'm going to talk about, I'm going to just use two studies in this as an example of what I'm talking about today. But the first study I'll talk about is using images, or well, both studies actually. The neural network that we used was trained on the Mura data set of upper musculoskeletal images for training convolutional neural network. We then put outputs or GradCam layer onto that as well to get this heat map type format. And we also had a text output, pathology, no pathology, in sort of binary format, and percentage confidence of the AI in the decision. So very, very briefly, there was 94 participants in this study. They were radiographers and student radiographers, and in the UK, radiographers would provide preliminary clinical evaluation on all images, and they would also provide formal reports as well. So I appreciate the sort of job role of a radiographer in the UK. It might be a little bit different internationally. So we presented 94 international participants actually for this study with a random allocation of 3 examinations. We asked them to make a decision on the pathological status. So is there pathology in this image? Yes or no, or maybe. And then they were given a heat map following each image presentation. And then after all, they were given the binary diagnosis. The AI in this study, as I say, was trained on Mura, but then was given a clinical data set. It was not a generalizable neural network, and it had an accuracy of about 57%. So it was a little bit rubbish, but that was intentional to sort of push the AI. We sort of did it intentionally then to produce AI results then that weren't that didn't perform very well, so that we could test the user. So the user diagnoses were gathered for each image, and t-tests and repeated measures ANOVA were done to calculate the accuracy or the agreement of the ground truth of the participants. And the impact of the AI feedback on the user was determined then by ANOVA tests then after that. So the t-tests were conducted across 4 conditions, either pathological or non-pathological, and the AI being correct or incorrect. And just to determine if there is an ability of the user to discern whether the AI feedback was correct or not. The ANOVA with post hoc tests, I'm not going to go into the statistics too much, but sort of gave us a bit of further clarity then on the findings. So basically the t-test found there was no difference in the student and radiographer group, but that might be due to the issues with the sample. The repeated measures ANOVA found that there was a statistically significant impact of the AI under 2 of the 4 conditions, so when the AI was correct, and in the pathological studies. And then post hoc analysis, that was limited use. The post hoc analysis was the important bit for us, and it clarified this with a bit more detail, and it found that there was an increase in performance, so agreement with ground truth, before feedback of the AI and after presentation of the final feedback. So it was beneficial to the users. In those pathological cases then, we actually found that the heat map was detrimental to the user agreement with diagnosis. So it was detrimental to assisting the user towards the correct diagnosis. And then the binary feedback then allowed them to recover to a point which was greater than their initial opinion. So there was a bit of correction there, but the heat map had a detrimental effect rather than a positive effect in the users. So we find also that the students were more likely than the radiographers to change their mind in response to any form of feedback, which is really supported by other studies. We really had expected that. And the response to binary feedback had a heavier reliance on this. So the direction of the decision switch then in a negative direction, so we're talking now about automation bias, was noted in the expected instances, and this supports the findings from the inferential statistics conducted earlier on. And again, we can see that that's more prevalent and more marked in the student group. So the other study that was very quick, but you'll be able to you'll be able to read the publication of that if you want a little bit more detail. But following on from this study, we got reporting radiographers, and these are radiographers who provide formal image interpretation, formal written image interpretation. So we recruited reporting radiographers from the UK, where this is established practice, to investigate the interaction of these experienced clinicians with artificial intelligence, because this is a group which research already demonstrates may have a high degree of algorithmic aversion and avoidance, and who have trust issues with technology, who tend to prefer their own opinion over that of AI. And the problem with that then is that they may not be able to leverage the benefits of AI. We use the Mura dataset images for this, and we can see that that there was some issues with this. We had to do a lot of initial screening of the images, and when we sort of looked into the images and found that a lot of them had sort of poor image quality. A lot of them were our AI was detecting sort of artifact and other things on the images. So we had to do an awful lot of work, a lot of cleaning of that data set before we were able to use it. So when we looked at the participant agreement, we nothing was really terribly unpredictable there. We did find that the users agreed, because we knew that although the AI wasn't generalizable, that it was good on the Mura data set. So it performed well on the data set that it was trained on, which isn't unexpected. So we find the most part users agreed, or either partly agreed with the AI diagnosis, and really only disagreed in very few cases. And we can see here actually the cases. I've highlighted the cases that the human and AI didn't agree. And interestingly, these were the cases where the participants said that the image quality was poor. So actually, do we know who was wrong? Was it the AI or was it the reporting radiographer? We really don't know that information. So there's a different picture with the heat map form of AI feedback, and there's agreement with the AI heat map in only 22% of cases. So here we're seeing this confounding issue with the heat map form of AI feedback rearing its head again in this group. So decision switching in this group was expected to be low. I'm not going to go into that much. Experienced clinicians tend to show a greater tendency towards algorithmic aversion, and there were very few isolated cases where they felt that the AI may either make them reconsider or change their mind entirely. So the focus of this study, as a recap, was the lack of trust of these clinicians, and we wanted to investigate whether there's a pattern of factors which may cause this, and the results demonstrated that it was the agreement, obviously, with the AI, with the AI and the user decision, which was the main contributing factor. But the bit I want to draw your attention to is the strength of the two significant findings, and that the large negative correlation there was between the agreement with image heat map and trust. So although the heat map caused confusion through these two studies with both types of either experienced or inexperienced users, that actually they sort of rated the heat map feedback as very important when they were establishing their trust in AI. So they're sort of looking for some kind of explainability, but the heat map may not be just hitting the nail on the head there with that. So from this, very, very briefly, this and a lot of other studies, we sort of started to think, well, there's an initial decision by the clinician. The clinician might then be provided with binary feedback based on our findings, and then some kind of multiple format AI explainability at the clinician preference and at the clinician timing as well, because there's we may find that timing becomes a very big issue too, where we need to think about avoiding the other biases that we're aware of, such as framing bias and satisfaction of search bias. If you're presented with AI feedback too early, how will that affect your decision making? And that is, we have doctoral level research going on in our team on that at the minute, so more to follow. This is just a little schema which I had produced a while ago, just for sort of general interest, but I'm a little bit short of time, so I'm not going to go through that at the minute. But as take-home messages, what I would like to sort of say to you in sort of a bit of a sort of bite-sized pieces is that care should be taken with data sets for training. Ask and critique when you're talking to a vendor. Ask them about their training data sets. What are they doing? Look at those papers that you're reading. Look into what data sets are they using. Do you know your stats? And Jordan sort of alluded to some of these, but do you know what F measure is? Do you know what dissimilarity coefficient is? Do you know what precision and recall is? So, if a paper tells you about a precision recall curve, you're going to know how that's different from a ROC curve, for instance. Prevalence, these are mostly prevalence agnostic measures. Is it maybe appropriate in some cases that a prevalence agnostic measure is not used? So know when those are appropriate. Have some scrutiny of testing. What is the performance based on when something's reported? Look into what that's actually based on. Question your own biases. the biases that you know and the biases that you don't know and the biases that might develop over time. Think about your experience level, think about your propensity to interact with technology. How might that impact your relationship and others' relationship with emerging technologies? And over the long term, what about complacency? What about skill loss? And skill loss is classified as sort of or sort of categorized as something which is terribly bad. And is it? I don't know. I mean, it's we're now using dictation software all the time. Maybe our typing skills are a little bit slower. We have to question, is that a bad thing? Has that freed you up then to do other tasks as well? I've included, Jordan, I've got a really, really comprehensive reading list for those who are interested. I'm not sure if that's a link that we can share, but I'm very happy to share it. And just a few sort of my own work, a few pieces of my own work, if that's of interest to everybody. And thank you so much for your time.
Wow, Dr. Rainey, thank you so much. That was a really fantastic lecture, and I apologize. We were having some volume issues over here
Oh
that I
no.
wasn't able, or I think that everyone else probably was able to hear just fine, but we were just not able to hear the very first
Oh,
portion
I'm
of it.
so sorry.
But I would be very happy to share the articles with the group, email those out to everyone, and send out
Okay,
the reading list as well.
no
Uh,
problem.
we have uh, a couple of questions in the Q&A, but I did want to ask in reference to the heat maps.
Mm.
I've seen some interesting publications on heat maps used to determine how algorithms that are in the training phase are making their decisions, and recall one very funny one that had a very high accuracy for detecting pneumonia on chest radiographs, but it found that in the heat maps that it was just looking to see if it was a supine image versus an upright
Yeah.
image. It was just playing the numbers game of, oh, this is a
Yeah.
portable radiograph. This patient is probably sicker. This probably has pneumonia.
Absolutely, and it does make you, I suppose, with being an HCI researcher, a human computer interaction researcher, when I hear things like that, and we sort of can think, oh, silly AI, but but when you think yourself, when you see a sort of, if you know that your scanner is in the emergency department, or, one particular scanner's in the emergency department and the other one's in the outpatient department, you sort of start to question, well, have I already got a bias in my mind about what I'm going to see in this image? Or because there was a study where I think it was on hip fractures. It was a number of years ago now, maybe 5 years ago or so, and it was a study on hip fractures, and the AI had they had learned the AI had learned the location of one of the scanner. One of the scanners was, I maybe can't, sorry, in a public forum, I shouldn't maybe say manufacturers, but one was manufacturer A and one was manufacturer B, and it learned that manufacturer A CT scanner was in the emergency department, and therefore it was detecting hip fractures. So it kind of hedged its bets, and
Oh, that's fascinating.
and, and it was really good. The performance was phenomenal.
I know it's very interesting. There's kind of shortcuts that AI can make to
Yeah,
make these
yeah.
to make these decisions.
Quite clever. We
Yeah.
don't want it to be, but it's quite clever.
Well,
Oh,
yeah. So we have a couple of questions in the Q&A that I'll address very briefly. So we have a question regarding the use of generative AI in
mm,
radiology. That is a great question. There's a lot of very different wide-ranging opportunities for the use of generative AI. Specifically, there have been some large number of publications and some very good publications about the use of ChatGPT and expanding our capabilities with natural language processing and clinical decision making.
mm,
We have a really great lecture on the use of ChatGPT in radiology from our intermediate level course that's available on our YouTube channel. And I should have mentioned this during our introductory lecture. All of these lectures will be recorded and available for free on our YouTube channel after this course is concluded. And I will be sure to send out that link to everyone after the courses or after those lectures are available. So if you want to learn more about the application of AI in different subspecialties, or if there are different special topics that you're interested in, please do check out our YouTube channel, and we'll hopefully have a good amount of information there for you. But I am going to go ahead. I think that we have reached the end of our time here. Dr. Rainey, thank you so much for such an excellent lecture today. And I look forward to getting to continue to work together, get to continue with
Yeah.
our topics in the future.
Brilliant. Thank you very much, Dr. Pershing. And thank you so much for everybody attending today as well. I hope that was interesting. Thank you. All the best.